We have Raphaël Ponge from Sichuan University to give us a talk. Raphaël Ponge is a distinguished professor at Sichuan University since 2019. He received his PhD from University of Paris-Saclay under the supervision of Professor Alain Connes. His research interests include non-commutative geometry, global analysis, pseudo-differential operators, cyclic homology, and classical analysis. He will talk about non-commutative geometry and classical analysis today. Let's welcome.
All right, thank you. Thank you for the welcome, and thank you for the opportunity to speak in this colloquium. So my talk will be about the interaction between non-commutative geometry and semiclassical analysis. So I will explain a bit what are these topics, but they are both topics within the larger topic of quantum theory, and it's only recently that we got some bridges between these two topics. And all right, so I start with a semiclassical analysis. So quantum mechanics is governed by the Schrödinger equations. So that's a Schrödinger equation on Rn, where here delta is a Laplace operator. So I take the Laplace operator to be positive. And okay. So V is a function of the potential. Right, and so H bar here is the Planck constant. And semiclassical, so on that is that we should recover, classical mechanics from quantum mechanics by letting the Planck constant going to 0. And so taking a Planck constant to go to 0 is called taking a semiclassical limit. And semiclassical analysis aims at looking at the spectrum or looking at the spectrum. So the goal of semiclassical analysis is to understand the behavior of the spectrum of Schrödinger operator when you let the Planck constant go to 0. So what we will be focusing on this talk is a semiclassical Weyl law. So okay, so that's a semiclassical Weyl law. So the goal, it gives a behavior of the number of negative eigenvalues of a Schrödinger operator under the limit, semiclassical limit h going to 0. So here, throughout this talk, if you have self-adjoint operator with discrete negative spectrum, n minus 1h is the number of negative eigenvalues of h. And for Schrödinger operator on Rn, the number for physicists, the number of negative eigenvalue correspond to the number of bound state. So in this slide, I'm stating the semiclassical Weyl law for on closed Riemannian manifold, that is a Riemannian manifold without boundary. But I also have a version on Rn or on domain of Rn, where it takes the Laplacian with a Dirichlet-Hornemann boundary condition. So the statement is as follows. So if V is a continuous real-valued functions on M, so look at the number of negative eigenvalue of h squared delta G plus V. So delta G is the Laplacian on M, associated with a Riemannian metric G. Okay? So we look at the number of negative eigenvalues. And under the semiclassical limit, that is when h goes to 0, this is like h to the, behave like h to the minus n. So more precisely, if you multiply by h to the n, this has a limit as h goes to 0, which is an integral of some power of the negative part of it. So the limit depends only on the negative part of it. And more generally, you can consider a fractional Schrödinger operator, where you replace the Laplacians by some power of the Laplacian. And again, you get semiclassical Weyl law, and the limit to get from the this law is that this integral, which of some power of the negative part of it. Here, d nu g, this is the Riemannian motion. All right. So there are various ways of proving the semiclassical Weyl law. So one way which is to use the Biermann-Schwinger principle. And the Biermann-Schwinger principle reduces the verification of the semiclassical Weyl law to proving Weyl law for negative eigenvalue of some compact operators. So more precisely, again, so H is bounded from below as discrete negative spectrum, denoted by n-1h, the number of negative eigenvalues of H with duplicity. And so, like I said, this Biermann-Schwinger principle relates semiclassical Weyl law to asymptotic for eigenvalue of compact operator. But if you have a self-adjoint compact operator, you can look at its positive and negative eigenvalues, or if you like, at the eigenvalues of the positive part or the negative part. All right, and the Biermann-Schwinger principle is as follows. So suppose you have a non-negative operator, S0, and a self-adjoint operator, V. So you don't assume that they are bounded, but you assume that if you take the compression of V by S0 to the minus 1/2, or if you want to be more rigorous, take S0 plus epsilon to the minus 1/2, you require this to be compact. So in this case, if it's compact, it's going to get that S square S0 plus V is going to have a discrete negative spectrum. So LP infinity, so here we have to assume more that just compactness. And all right. So is not familiar with Banach space theory. LP infinity, this corresponds to the compact operator, such that the eigenvalues of absolute value of t are like big O of j to the minus 1 over p. Okay. So this is a condition on the order of decay of the eigenvalues of the Biermann-Schwinger operator S0 minus 1/2 V S0 minus 1/2. So if you have that, then you get that existence of a limit for H2P number of negative eigenvalue of H squared S0 plus V as H goes to 0 is equivalent to existence of a limit for J times lambda J minus of S0 minus 1/2 V H0 minus 1/2 to the P. And it sounds that if one limit exists, the other exists, and if they exist, then they are both equal. So this reduces the problem of establishing a semiclassical Weyl law to proving a Weyl law for a negative eigenvalue of this compact operator S0 minus 1/2 V S0 minus 1/2. And one advantage of this approach is that you have LP infinity. This is the topology, and because it has a topology, you can apply some perturbation theory to extend, for instance, this result to potential that are not continuous. So that's yeah. What I mean is that so when I stated the semiclassical Weyl law, you have continuous potentials, and by using the Biermann-Schwinger principle, and the fact that you interpret this as a limit for compact operator, you can apply perturbation theory here within the space of LP infinity to extend the semiclassical Weyl law. two potentials that are not continuous, they are just LP. All right. So this is one motivation for the main motivation for using the Biermann-Schwinger principle. Okay. And how does it prove how does it get semiclassical Weyl law? So we use the result of Biermann-Solomyak from the 70s. We say that f is a continuous real-valued function, q is positive. Then I actually have a Weyl law for the positive and negative eigenvalue of the Biermann-Schwinger operator, delta G minus Q over 4, F delta G minus Q over 4. So if you take, multiply lambda J plus or minus by J to the Q over N, and let J goes to infinity, this converges to some power of the integral of the inverse power of the positive or negative part of F. And if you combine this with the Biermann-Schwinger principle, then I will get a semiclassical Weyl law. So the first line is here, this is the Biermann-Schwinger principles. And to get from here to here, you just apply the result of Biermann-Solomyak. So that's the way I can get semiclassical Weyl law. And I will see this actually, this approach works in a very large setup of non-commutative spaces. So precisely, we'll get a semiclassical Weyl law in non-commutative geometry. So let me briefly explain the main objective of non-commutative geometry. So one of the main objectives is to translate the main tool of Riemannian geometry into the language of operator of quantum mechanics. So quantum mechanics relies on a Hilbert space formalism. So we like to translate the tools of Riemannian geometry in terms of operators. And so one goal is to provide a common framework for quantum mechanics and general relativity. And but more generally, non-commutative geometry can provide a mathematical framework to deal with a variety of geometric problems whose non-commutativity prevents us from using standard tool from differential geometry. So, for instance, when you look at the action of Z on the circle by irrational rotations, the quotient space, the orbit space, the orbits of this, if you act by irrational rotation, the orbits are dense, and so it means that the orbit space is not even Hausdorff. So if you like, using non-commutative geometry, you can even do some differential geometry on spaces that are not even Hausdorff. And this is based on general principles, comes from the work of Gelfand. So the Gelfand transform gives a one-to-one correspondence between locally compact species and commutative system. So for instance, so it goes as follows. So locally compact species, you can associate a system algebra of continuous function next vanishing at infinity, and you actually have an inverse map. So we give one-to-one correspondence between locally compact species and commutative system algebra. So we can see commutative system algebra are non-commutative topological space, or at least non-commutative locally compact species. And then more generally, you can think of system algebra as algebra of function on non-commutative spaces. So that's what you get at the level of topology, and at the level of differential geometry, non-commutative manifold, or the analog. I mean, what plays a role of manifold in the setup of non-commutative geometry? This is notion of spectral triple. So what's a spectral triple? So I give a definition. I will present some examples in the next couple of slides. So spectral triple consists of triple AHD where H is a separable Hilbert space, A is a unital star algebra of L of H, or if you like, you can think of A as a star subalgebra which is unital. It should be represented by bonded operator on H. Okay? So if you take the closure of A, this will be a C-star algebra still with a non-commutative space. Okay? And the geometry is encoded like by the third piece of data, which is an self-adjoint operator D with compact resolvent, and so that it commutes with element of algebra A up to a bonded operator. So I'll give examples of spectral triple in the next two slides. What play a role of dimension is notion of P summability. So you say that the spectral triple is P summable if the eigenvalue of the absolute value of the resolvent are like big O of j to the minus 1 of P. So that means is that the resolvent for d to minus 1 is actually in this Weak-Shelton class at P infinity. In practice, what it means is that if you take trace to the d to minus q, this will be, so d to the minus q will be a trace class for all q greater than p. And as I mentioned, this degree of summability is some kind of analog of the notion of dimension for spectral triple. So let me give a few examples of spectral triple. So if you start with a domain, a bonded domain in Rn with smooth boundary, you can get spectral triple by using the Dirichlet or Neumann Laplacian. So here, all my Laplacians are positive. Okay? And so you get what we have. Okay, so operator is given by the square root of the Dirichlet or Neumann Laplacians. And so you have algebra of smooth function with compact support. And so they act by multiplication operator on L2 of omega. Hilbert space of L2 function on omega. So CC infinity, in fact, we can take CC, you can replace CC, okay. And can also check that they commute with CC infinity, commute with square root of delta up to bonded operator. In fact, what you're going to get is a differential operator of order 0, which is bonded. And well, this is not unital algebra. Okay, so to get unital, you add the constant. Right, so that's an instance of spectral triple. You can also get spectral triple from closed Riemannian manifold. So where instead of using Dirichlet of Neumann Laplacian, you can use the Laplace-Beltrami operator. Okay, so D star D. And here take the algebra of smooth function on M, which I by bonded multiplication operator on L2M. So here close means compact without boundary. So all the functions in CC infinity are bonded, so they act by bonded multiplication operator on L2 omega. And CC infinity commute with square root of G, the CC infinity commute with square root of delta G up to bonded operator. Okay, so the commutator of a smooth function with square root of delta G is a differential operator of order 0, which is bonded. For non-commutative geometry, we're actually more interested by replacing square root delta G by a differential operator, and more specifically by the Dirac operator. Okay. So in this case, we take a Dirac operator. You have to replace L2M function M by the Hilbert space of L2 functions of L2 spin. Anyway, for this talk, I will be interested only by square root of Laplace type operator. And so now I can state the main result. So consider a spectral triple AHD, which is P summable with P positive. So P can be any positive number, and we need a condition to get semiclassical Weyl law. So this will be Tauberian conditions, and all right. So namely, consider so the fact that it is P summable ensures that each minus t d square is trace class, and so if take an element A of algebra script A, so this would be imply A to the et d square will be still a trace class for all t positive. So we take the trace and require that as t goes to 0, this will be like t to the minus p over 2 times some coefficient which is denoted to A. It also requires to have a lower order remainder. So this Tauberian condition is satisfied in numerous examples. So we'll see at least a few of them. And now if we have that, then can we get Weyl law for Biermann for those Biermann-Shroedinger type operator. So d to the minus q root 2a, d to the minus q root 2. So if look at the positive or negative value, and multiply by j to the q over p as j goes to infinity. This converges to some power of tau of inverse power of positive or negative part of it. So here, when you work with algebra, the positive and negative parts are defined as follows. So A plus minus is 1/2 of absolute value of A plus or minus. All right. And so this means that you have a Weyl law for positive or negative eigenvalue of Biermann-Shroedinger operator. And we know that by the Biermann-Shroedinger principle that this implies a semiclassical Weyl law. So namely, for all V or self-adjoint element of A bar. Okay, so I forgot to mention that A bar, this is a closure of A in L of H. So if you like, this is a C-star algebra generated by A. So for any self-adjoint element of A bar, for every positive Q, if you look at the number of negative eigenvalue of H2Q d square Q plus V multiplied by H and P, this, as H goes to 0, this converges to tau of some power of the negative part. All right. So as mentioned, the second part follows from the first part. So what we need to prove here is only the first part. In fact, well, I won't really elaborate on this, but even the first part has other application besides applying semiclassical Weyl. Right. So this improved previous result of McDonald-Sukochev-Zanin. The main improvement is that in their work we assume p summability with p greater than 2. So p summability, as mentioned, corresponds to notion of dimension. So you assume p greater than 2, you exclude two-dimensional and one-dimensional examples. So in particular, an important class of non-commutative examples is provided by non-commutative tori. And so you exclude the approach of McDonald-Zanin excludes non-commutative two tori, which are the most important examples. I mean, which is maybe the most, which are maybe the most important instance of quantum tori. One other improvement was that replace. So McDonald-Sukochev-Zanin use another Tauberian condition, which is maybe not so standard. And it was a question of Connes in online seminar to replace their Tauberian condition by a more standard Tauberian conditions. And this is a Tauberian condition that is easier to check. So this, in fact, this condition is satisfied in numerous examples. All right, so I just want to explain how you recover the usual semiclassical Weyl law from this framework. So first, you can look at a domain in Rn, only domain with smooth boundary, and take delta to be the Dirichlet or Neumann Laplacians. So it can be shown that, so we know that if you take the square root of delta, you get a spectral triples, where algebra is CC infinity plus constant. And so to apply the semiclassical Weyl law in for spectral triple, that is the main result presented, we need a Tauberian condition. But this Tauberian condition has been known for quite some time. This goes back to a result of Karman and published in 1934, and result of Meenakshi-Sundaram, which was published in 1949. So namely, take every continuous function, function continuous up to the boundary. So that's how we include the closure of this algebra. We get that trace of f to the e to minus t delta is like t to minus n over 2 times integral of f. And you also have a remainder term. So big O of t to minus n over 2 plus 1. But in fact, the work of Karman and Meenakshi-Sundaram gives a full asymptotics as t goes to 0. Okay. Right. So this was used, the result of, I don't know about Karman, but at least Meenakshi-Sundaram, this was used to give a proof of classical Weyl law for Dirichlet and Neumann Laplacian. And so, all right. So we have a spectral triple that satisfies the Tauberian condition of the result I presented before. So we get, so we may apply this result. And what you do is that you recover semiclassical Weyl law for a bounded domain with Dirichlet or Neumann condition. So here it takes the following form. So if these are continuous real valued functions, continuous up to the boundary, Q is any positive number. Look at the number of negative eigenvalue of h2q delta q plus v by h to the n. This converges as h to 0 to the integral of some power of the negative part of it. Okay. So we see that by using a result I presented, we recover the semiclassical Weyl law from the result of Karman and Meenakshi-Sundaram from the 30s and 40s. Okay. So you can repeat, you also have the same, you can do the same thing for closed Riemannian manifold. So you have take a square root of the, so consider a closed Riemannian manifold, Mg, take the square root of the Laplacian define a spectral triple. And so the Tauberian condition here follows from the result of Meenakshi-Sundaram Pleyel from 49, where, so namely, if f is any continuous function, trace of f to the e to minus t delta g is t to minus n over 2 times the integral of f against the Riemannian measure. And you have a remainder term, which is big O of t to the minus n over 2 plus 1. But in fact, you have a full asymptotics. And so what's important is that the terms, various terms in Paris asymptotics are related to curvature invariant. All right. So this result was used by Meenakshi-Sundaram to give, I think, was probably the first proof of the classical Weyl law for Riemannian, for Laplacians on closed Riemannian manifold. In any case, so you have spectral triple, and Tauberian condition is satisfied. So if you apply semiclassical Weyl law in non-commutative geometry, you recover the semiclassical Weyl law in Riemannian geometry. So namely, for every continuous real valued potential, every positive Q. If you look at number of negative eigenvalue of h2q delta gq plus v implied by h to the n, as h goes to 0, this converges to an integral of some power of the negative part of v against the Riemannian motion. Okay. So that settles the previous case. Well, previous instances of semiclassical Weyl law. But you can use the semiclassical Weyl law in non-commutative geometry to get to prove semiclassical Weyl law in new setting. So one setting I will focus in this colloquium. Okay. Okay, so just this is setting of contact geometry. So what's a contact manifold? So for one thing, contact manifold are some kind of odd-dimensional version of symplectic manifold. So consider here a closed-oriented manifold of odd dimension 2n+1. And so the contact structure is given by a contact distribution. So this will be a field of hyperplane in the tangent bundle. Or if you like, this is given by the kernel of one form. So H is kernel of theta. And this one form is contact means that if you look at theta wedge d theta n, this will be nowhere 0. And in fact, since it's oriented, you can assume this is actually a volume form. All right. So since so this implies in particular that d theta is non-degenerate if you restrict it to H. And so in particular, you can find an almost complex structure such that d theta, such that you can get a metric out of d theta and J. And then you can get a Riemannian metric, which is theta square plus d theta dot J dot, okay, on T. So it's called a Levy metric. And the volume form of respect to G theta is theta is precisely theta wedge d theta n up to some normalization, up to some scalar. All right. So we have numerous examples of contact manifold, particular odd-dimensional sphere contact. Heisenberg group is a contact manifold, and it's quotient by co-compact lattices. Also have a strictly pseudo-convex hypersurfaces in complex space. So that's another example is to take a sphere bundle of a positive Hermitian line bundle over a Keller manifold. So this appears in the context of quantization. Actually, a number of other settings in differential geometry. And if you take the cosphere bundle of, so you have an action of R, if you like R plus, well, R plus star on the fiber of T star M. And if you quotient by this action, you get the cosphere bundle. And this is so if you like on T star M, you have standard symplectic structure. And if you quotient by R plus star, you get the symplectic structure descend to a contact structure, if you like. So anyway, there are a bunch of examples of contact manifold. Okay. And okay, but what plays the roles of the Laplacians here is not is the sub-Laplacians. So I define the sub-Laplacians. So we take a horizontal differential which maps on smooth function to a section of H star that is horizontal forms. So basically, it works is that you take the differential and you restrict it to H. And the sub-Laplacian is basically d star H dH. So this works because you have can define the adjoint by using I don't really get to details. It works because you have a Riemannian metric. So you take adjoint with respect to the metric, the Levy metric G theta. Okay. All right. So the thing is that because you restrict to directions that are in H, you don't get the directions that are transverse to H. So it means that when you differentiate, when you apply the H, you miss some of the differentiation in directions that are transverse to H. And as a result, the sub-Laplacian can never be elliptic. Okay? So you cannot apply the usual elliptic calculus to study delta sub-Laplacian. But in fact, this is the result of Hermander and also for Landstein. Well, I mean, for this specific operator, contact case. So the result of Hermander is way more general. That the sub-Laplacian delta H and corresponding hit operator, so H acts on M cross R, are apolyptic. So it means, so here there are various notions of apolypticity. So here you see the minimal notion of apolypticity is that basically if delta H U is smooth near a point x0, then U is smooth near x0. Okay. So in fact, Hermander gives a result in terms of some Sobolev species, and for Landstein probably gave a result into a more suitable Sobolev species. So I don't, yeah. So the okay, and okay. So all right. Well, I should have put the boxes in opposite order. So this is a result that can show that if you take the square root of delta H, you're going to get spectral triple. All right. So So basically, you can there is a pseudodifferential calculus which is adapted to contact manifold. So it was constructed by Michael Taylor and Bix Greiner, and basically what I showed is that square root of the Laplacians is an operator of order 1 in this calculus, and therefore I was going to take a commutator of C infinity m with square root delta H. We get an operator of order 0 in the calculus of Taylor and Bix Greiner, and therefore since order 0 in the calculus it is point. Okay, so that's yeah. And you get the fact that it is 2n plus 2 summable as a consequence of this result of Bix Greiner and Taylor. So if take any, so basically it gives, so they establish short time asymptotic for the hit kernels of the sub-Laplacians. Okay, so full asymptotics. So this is a complete analog of the results that you have for Laplacian or Riemannian manifold. So, and here what we get, at least, is that take trace of f to the e to minus t delta h. So this will be like t to the minus n over 2 times some constant times the integral of f against the compact volume form, theta wedge d theta n. And then we have a lower order term, which is big O of t to the minus n. So this constant is given by z. So the thing is, well, so we get it because, in fact, the representation theory of the Heisenberg group comes into play. And so we end up by getting this constant. But the advantage of, but at least we have an explicit constant. Yes. So, so we have a spectral triple, and this satisfies Tauberian condition that we need to apply the semiclassical Weyl law in mathematical geometry. So as a result, we get a semiclassical Weyl law in contact geometry. So for every continuous real valued function on M, for every positive Q, if we look at the number of negative value of H2Q delta HQ plus V, and if we multiply by H to the 2n plus 2, as H goes to 0, this converges to gamma n, so a constant that I wrote down in the previous slide, times the integral of some power of the negative part of V against the volume form. So remark is that, so we have a semiclassical Weyl law in contact geometry. So note that in the Riemannian case, Riemannian, okay, if you take Riemannian manifold and then G, you're going to have semiclassical Weyl law for n h to the n, number of negative eigenvalue of h squared delta G plus G. Yeah. And here in the contact case, So here a manifold has odd dimension, 2n plus 1. So this is also H. Okay. Oh, H, which is curve of theta. We have a semiclassical Weiss law, which is of the form Hn plus 1. Sorry, it's H2n plus 2. Sorry. Well, I think people in the back, so H2n plus 2. N minus of H square delta H plus V. So remark here is that 2n plus 2 is actually, so dimension of manifold is 2n plus 1. So in the case, you have H to the n, so that's the dimension of the manifold. And here what you get as exponent of H is 2n plus 2, which is the dimension of m plus 1. And the reason of that is because the transverse direction actually can't double in a sense. And therefore, with respect to the Riemannian case, we get we have to add what actually plays a role of dimension. It's not the dimension of m. But what pop-ups is not dimension of m, but it's dimension of m plus 1. In the sense that's consequence of partially of the hypolepsity. So now I would like to explain that in fact we can work in an even more general, we can get a semiclassical Weiss law in an even more general setting, which is a setting of sub-Riemannian geometry. So consider, so what's a sub-Riemannian structure? So consider, so M is a closed manifold, and H is a sub-bundle of the tangent bundle. Okay, so we satisfied an extra conditions called a bracket condition that I will explain in a few seconds. And GH is a field of inner product on H. So what's when you look at the probably the best is we may assume at least locally that that H is generated by a vector field. Okay, and then you can consider, so that will be H1. And look at H2, which will be H1 plus the bracket of element of the bracket of vector field with value in H. So that will be H1 plus X1, X2, X1, X3, etc. Okay. And you repeat this, H3, so this will be H2 plus H, the bracket of H vector fields with value in H with vector fields in H2. So it will be H2 plus bracket of so threefold the bracket Xi and Xk. And you can repeat all this. So that will give you get a chain of distribution, so an increasing chain of distributions. Okay. And the bracket, so this is true if you start with any sub-bundle of tangent bundle. And the bracket condition, so that states that, requires that this chain is going to be finite and going to reach Tm at some point. So we can find R such that HR is equal to Tm. Okay. So it exactly means that Tm is spanned by, at every point, Tm is spanned by the bracket of vector fields with value in H. And the equiregularity condition that I'm going to add is that this distribution. So this definition I give here is actually as a module of submodules of the module of. Okay, so this H1 is okay. So H2, H3, H4, etc. are actually the way I wrote on the board. So these are submodules of the modules of vector fields. And the equiregularity condition is that this is actually a module of section of some sub-bundles of T. So if you like, so exactly, so if you like, I can write HWX, which would be a set of xi x, xi h2x, hi span of hix, and hi and hkx. So technically, this is a sub-bundle of a tangent space X, and you can also define H3X as follows. X, Hi, SJX, Hi, XJ, HK, X, etc. And so you require that so the dimension may depend on X, and you require the dimension does not depend on X. And this exactly means that H2, H3, H4, etc. are actually a module of section of some sub-bundles of T. All right. All right. So you have a number of examples. So contact manifold are instances of Sub-Riemannian manifold. So you get Sub-Riemannian structure on graded nipotent Lie group. So for instance, as a Baire group. So actually, in manifold should be quotient of graded nipotent Lie group by co-compact lattices. Contact manifold are, as I said, instances of Sub-Riemannian manifold. And you have various generalization of contact manifold, and there are also Sub-Riemannian manifold. Look at real hypersurfaces in OCN. So real hypersurfaces, so that will be a sub-Riemannian structure in the sense that the bracket condition is satisfied, but this need not be equiregular. And you have numerous over, well, you have one area of symmetric spaces, and you have many other examples which occur in geometry, PDE, applied mathematics, and various real-life situations. So these are some applications. Okay, so in same way as in the contact case, what plays the role of the Laplacian is the sub-Laplacians, and you can define the sub-Laplacian in the same way as in the contact case. So basically, you take you restrict define the horizontal differential by restricting the differential to the horizontal direction, that is direction h, and then define the sub-Laplacian as dh star or dh. And again, unless h is the whole tangent bundle, the sub-Laplacian is never elliptic. However, it is apolliptic by result of Hollander. So in fact, the result of Hollander, you only requires to have the bracket conditions. So if the bracket condition holds, then the sub-Laplacians and the hit operator are apolliptic. So that is, if delta HU is smooth near x0, then U is smooth near x0. And in fact, get the result in terms of some Sobolev estimate, which was provided by Hollander. So what play roles of the dimension? I say in contact case, what you get is that the horizontal so the dimension that's going to pop up is in contact case is the dimension of m plus 1. And it's the dimension of m plus 1 because direction transverse to h can't double. So more generally, you find a sub-Riemannian dimension as some kind of weighted dimensions where you count that elements which are in HW but not in HW minus 1 have weight W. So it takes the so I should write here. So that will be so Q will be so you get this filtration H1 which is H, H2, H3, etc. And at some point you reach share which is TA. So Q is basically as follows. So amount of H1 I weight 1, so it takes dimension of H1. So the amount of H2 that are not in H1 are weight 2, so you take 2 dimension of H2 minus dimension of H1. Now you want reaction in H3 that are not in H2 have weight 3, so you get 3 dimension of H3 minus dimension of H2, and you keep on doing that, so you get R minus 1 dimension of HR minus dimension of HR minus, sorry, it should be R. And this dimension appears, so there are different ways to interpret this dimension. So when you have some Riemannian structure, you can define a metric, which is called a Carnot-Carateri metric. Okay, and by considering, so we define the metric like for the Riemannian metric, except that instead of considering all paths joining 2 points, we consider only paths that are tangent to H. So we have this natural metric, and you can show that the Hausdorff dimension with respect to this metric is precisely the sub-Riemannian dimension. And from a spectral theoretic point of view, from an institute point of view, this dimension appears when you look at the heat kernel asymptotic for the sub-Laplacian. So that's a result that goes back to Benarus and Leon from the 80s. So if take f smooth function, and as as t goes to 0, look at trace of f to the h minus t delta h. So this would be like t to the minus q over 2, where q is a sub-Riemannian dimension. And you have a lower elemental term, which is because of t to the minus 1 over q. All right. So now you have extra terms with respect to the Riemannian cases. So one term comes from gamma delta h, which is some functions. So, well, you get it from, so what's happening is that at every point, you can approximate the sub-Riemannian structure by a sub-Riemannian structure on some group, which is an nilpotent graded group. Okay, so it's called tangent group or tangent cone or Ciatin group, depending which background come from. Okay, and basically you're going to construct parametrics for the heat operator in terms of by using a fundamental solution for the heat operator on the tangent. So And then you have another term, which is a measure. It's called a pop measure, which is a mechanical measure associated with Sub-Riemannian. So the point is that you can compute the leading terms in the asymptotic from computations of the fundamental solution for some hit operator. So that means that at every point you can compute the terms in the you can compute the density gamma delta h from the fundamental from computation of the fundamental solution on the on some nilpotent quadratic group. So the issue is that there are only a few examples where you have explicit formula for this fundamental solution. But right. But in a way, you have some formula. Okay, so this shows that you have some Tauberian conditions for some spectral triple, and that spectral triple is also given by the square root of delta. Okay, so maybe let me go back for the credit. So Benarus-Leon proved this in the 80s using stochastic calculus. David is more recent. It's from early 2000. Was from maybe 7 years ago. This is by using some differential calculus. And Colin de Verdière, Hilary Trella, so it's more recent papers. I mention it because, in fact, Benarus, Leon, de Verdière, this is in the equiregular case, but Colin de Verdière, Hilary Trella, they prove it in the non-equiregular case. That is when you have jump of dimension and this distribution. Okay. All right. So yeah, so you have a spectral triple by using the square root of the Laplacians. So that follows from result of David. And this is Q summable, where Q is a sub-Riemannian dimension. So you have spectral triple and you have a Tauberian condition. So you get semiclassical Weyl law. So if you apply semiclassical Weyl law in CG, in quantity geometry, you get semiclassical Weyl law in sub-Riemannian geometry. So in the following form. So if V is any continuous real value functions, Q is any positive number. If you look at the number of negative eigenvalue of h to q delta h q plus v multiplied by h to the q, as h goes to 0, this converges to integral of some power of the negative part of v against, so this gamma delta h x, which is the density, and here we have this pop measure. So you have a semiclassical Weyl law for sub-Riemannian manifold, at least when you have this equireality condition. In fact, you can extend this result to even can remove the equireality condition in some instances by using a result of Colin-Verdière, Hilary Trella. So Colin-Verdière, Hilary Trella gives the Tauberian conditions, and you can also use a result of Andrei-Lidakis motion Lincoln to show that you have spectral triples even when it's not equiregular. And a result. So I just give one example. If you look at the boundary Grushin operator on the two torus, so this is x squared plus y squared, where x is dx and y is 2 1 minus cos x dy. So of course, when x when 1 minus cos x when x is different from 0, 1 minus cos x is non-zero, and so you get a positive you get a non-zero multiple of, actually even positive multiple of dy, and so in this case, x and y span the whole tangent space of two torus. However, you have a singularity at x equal 0, okay? And so you get that the distribution defined by x and y is singular on the 0 cross t. Okay? And what's happening here is that when you look at the kernel asymptotics and henceforth in the semiclassical Weyl law, you have a competition between contribution coming from the regular part and the singular part. Okay, so which gives a different exponent. And this example This is a singular part gives the stronger exponent, and so we get semiclassical Weyl law, where the limit actually are localized on the supported on the singular part of it. Okay. So if you look, so for every continuous function on the two torus with real value, just take a number negative eigenvalue of h squared delta plus v. So delta is actually a sublation h squared plus y squared divided by h cubed. As h goes to 0, this has a limit, which is an integral over the singular part. So this is a 0t, so that's integral over t. So the negative part of v restricted to the singular part to the power of 3. And c is a constant, which is computable, but I haven't computed yet. Okay. Actually, I haven't written the paper yet. When I write the paper, constant will be computed. And that's it. And thank you very much for your attention.
Any question? Okay, I would like to ask some questions. First of all, I found that the capital P or capital Q are integers.
Yes.
Right? Is it possible to find an example such that the Q, the dimension, SR dimension could be like a fraction or something else?
Yeah, so for spectral triple, yeah, I think you have instances when you look at fractals. So this is in the book of Connes, actually. Okay. And there's a work of Connes, Sullivan, and later a work of Connes, Zanin, and Sukochev.
Yeah, also another question. You used V minus here.
Yes.
What happened for the V plus?
Well, the thing is, okay. Delta is positive, so since delta is positive, the positive part does not.
Okay, already admitted.
Yeah.
Nice. Any other question? Okay, if not, let's thank Professor Ponge's wonderful talk again.
Thank you.